You may have already learned that correlation does not imply causation. This phrase is repeated so often because it is very tempting to infer a causal relationship when two variables are correlated. However, a correlation only allows us to conclude that two variables covary to some degree. It is possible that there is no causal relationship between them at all, or that the causal relationship that does exist is more complex. Among statisticians, headline writers are famous, or maybe we should say infamous, for the many times they have implied a causal conclusion from a correlational result. For example, take the headline, "Having a strong life purpose eases loneliness of COVID-19 isolation, study finds." This headline was based on a study that observed a correlation between feelings of life purpose and feelings of loneliness. Now, it may be that having a strong feeling of purpose in life really does cause people to feel less lonely when they are isolated. However, it could be that people who feel less lonely during isolation are more likely to develop a strong feeling of life purpose. Or, it could be that some other factor influences both purposefulness and loneliness. Maybe both variables are influenced by emotional intelligence. If the researchers have not measured emotional intelligence, they may have no idea that this third variable is causing the relationship between feelings of purpose and feelings of loneliness. In general, when two variables A and B are correlated, we must consider all these possible explanations of the cause of the relationship. Because neither variable is under the researcher's control, it is not possible to determine whether changes in variable A cause changes in variable B, or changes in variable B cause changes in variable A, or whether a third variable causes the changes in A and B. When there is a third variable such as variable C in this last case, that variable is called a confounding variable because it is not accounted for by the data, even though it may explain the relationship between variables A and B. These problems might have you wondering, well then, why study correlations at all? One reason is that although correlation does not imply causation, the reverse is true. Causation does imply correlation. If A causes B, then A and B must be correlated. So if a theory proposes any kind of causal connection between A and B, then it makes sense to test for a correlation between A and B. Also, other factors can sometimes help us reason our way around some of the problems in interpreting a correlation. For example, the heights of children are correlated with the heights of their parents. There is no plausible way that a child's height could determine the parent's height, so we do not have to worry about the direction of causation in this case. Of course, it is still possible that the heights of parents and offspring are influenced by other factors like genetics and socioeconomic status. It is also possible sometimes to statistically control for the influence of other confounding variables. These statistical methods, including what is known as partial correlation, can help us address some of the problems with interpreting a correlational result. So, correlational measures are an important part of a psychologist's statistical toolbox. These techniques are used to study many variables that would be unethical or difficult to manipulate directly. Correlational analyses are also used in assessments of the reliability and validity of psychological tests and measures.